Hello everybody and welcome to another machine learning with Scikit-learn in Python tutorial video. In this video and the subsequent videos we're going to be kind of shifting gears a little bit and talking about unsupervised machine learning. So in the videos leading up to this video we were covering supervised machine learning, specifically using a support vector machine, even more specifically using linear SVC. So that was just a really basic example of supervised machine learning. By no means do we cover everything involved with supervised machine learning or anything like that, but we just wanted to cover the basics of a project or a type of problem that we might use supervised machine learning for. So now we're going to be talking about unsupervised machine learning. And it's really not too confusing. The difference between supervised and unsupervised machine learning is whether or not we, the scientists, are providing the computer with labeled data. Most of the time you're going to be using unlabeled data entirely where you don't even know the correct answer. The only time you're going to really use labeled data with an unsupervised machine learning algorithm is going to be when maybe you're just trying to test that algorithm. But for the most part, you aren't even going to know the answer. So what kind of problems are we applying unsupervised machine learning to? Well, we can actually apply problems, or we can apply unsupervised machine learning to supervised machine learning problems. So we could actually use unsupervised machine learning on, say, the stocks question and see if we could separate them into two groups. Now, those two groups that we separated them into, we may or may not be they may or not be underperforming or outperforming groups. They would just be two groups. So that leads me to the next point with unsupervised machine learning. Unsupervised machine learning is separated into two kind of dichotomies as well. The first one is where, well, both of them, the targets is to cluster data into groups. So sometimes you'll hear it called cluster analysis or whatever. But with unsupervised machine learning, you've got two options here. You either throw a bunch of data at the machine and you expect the machine to just kind of figure it out for you, or you throw a bunch of data at the machine and you ask it to separate the data into X amount of categories. So an example might be you throw a bunch of pictures of males and females at the computer and you say, separate this please into two categories, with the goal of hopefully it separates the pictures by male and female, and then what you can do is you can derive the underlying major differences between a male and a female's face in a picture. So that would be an example of what is known as flat unsupervised learning or flat categorization or flat clustering. The other one is going to be hierarchical clustering, and that is where you feed a bunch of data to the machine learning algorithm and you let it determine how many clusters there ought to be. So either of these is doable, and they're both unsupervised machine learning. Obviously, taking the, not telling the machine how many categories there are, that's even more unsupervised like than telling it how many categories there are, but obviously we both of them are unsupervised examples. So what I'd like to do is show an example of each of those here. So first we'll do just a flat clustering where we specify some data and we tell the machine, hey, this is how many categories I'd like you to separate this data into. So before we do that, just some quick examples. The one that I just covered basically with separating maybe male and female faces, that's an example of one where we would do, that's a flat cluster. Some hierarchical clustering might be used for, say, genomics, something like that, where basically unsupervised machine learning, the general point of using that is to understand or derive some sort of underlying structure behind something that we don't quite understand yet. So it's used in like genomics and stuff like that because we don't really know the structure or how they work with each other, the genes, I mean, and so we use unsupervised machine learning to help hopefully gather some insights. Now there is one more reason why unsupervised machine learning is used, and that is actually to bring down or simplify a data set into a way that either we can visualize it or at least better understand it. And so like if we take, for example, this dog in the background, this dog has a lot of features. He's got fur and legs and a face and a nose and eyes. He's got, and then we could go even further, he's got strands of fur or hair or whatever, and then even further he's got cells, and those cells have nucleuses and all this kind of stuff, nuclei. And so we have to understand that there are a lot of features to a dog, and initially feeding in every single feature of something, we might weigh every feature as, how do we weigh the features in terms of importance? And so actually what we can do is we can use unsupervised machine learning. We can feed through the features of a dog, let's say, and the features of a cat, and we can have all of those features, and then some of those features are very similar to each other, yet some are very, vastly different. And so we can use unsupervised machine learning to actually take all of the features of dogs, all of the features of cats, and kind of simplify all of our features into maybe 2 or 3 features maximum by kind of making conglomerates or picking out the ones that actually matter. And there's a specific term for that, but we'll talk about that later. But yeah, so that's another third kind of example of what we might actually use unsupervised machine learning for. So anyways, with that, let's go ahead and hop into the first example that we're going to do, and that's again going to be just flat clustering. So first we're going to go ahead and import, well, I was going to import time, but I don't really think it's necessary in this one. So anyways, import Numpy, however, as NP, and if you're following along in this actual entire machine learning series, if you're not, that's okay, but if you are, we're going to use the exact same data as we used for the initial, actually both the linear SVC example and the SVM example that we use. So it should look fairly familiar. We can use that data for this one. For the hierarchical clustering, we'll actually end up having to make a new data set because it's not possible to do it with the data that we have. Anyway, so we're going to import Numpy as NP, and this is purely so we can convert our data set to something that is acceptable by Scikit-learn. Next, we're going to, from matplotlib, import, or actually, I always do it this way, import matplotlib.pyplot as plt. Then we're going to go from matplotlib, import style, and style.use ggplot. If you're on Python, say 2.7 or with an unupgraded version of matplotlib, you can feel free to ignore these 2 lines. It is just to make the graph look a little prettier, nothing more. So feel free to ignore them if you don't have a current version of matplotlib. Next, we're going to import the actual machine learning algorithm from Scikit-learn. So we're going to go from sklearn.cluster, import KMeans. So for now, our cluster, or our, cluster. For now, our example is going to have few enough data points that we can use KMeans. If you have more than, say, 10,000 data points, you'll want to use KMeans mini batch, which what that's going to do is going to separate your data into a bunch of little batches of the data, because anything over 10,000, it's going to get, things are going to get hairy. So anyway, we import KMeans, and now we're ready to make a data set. So again, I assume, or I expect that many people might actually view this video without viewing the other one. So first, let's draw out our data and kind of see what the data is that we're working with, and then we'll go from there. So we're going to create a scatter plot. We've got x coordinates, y coordinates, and we're going to use the same data as we had used before. That data was, for x, we had a 1, a 5, a 1.5, 8, 1, and 9. That's our x coordinates. Now for y coordinates, we'll have a 2, an 8, a 1.8, another 8, a 0.6, and an 11. Then we're just going to call plt.scatter, and we're going to scatter x and y, and then we're going to run plt.show, and that will bring up the plot for us. Obviously, you're going to need matplotlib if you don't have it, Numpy, and of course, Scikit-learn. If you want to know how to get all that stuff, just check out probably the first video in this entire series, or just go to the respective websites for those modules and install them. So this is the data that we're working with here, and as you can see, probably with your eyeballs, if you were gonna, be given the task to cluster these, you would probably say, okay, we would cluster these top 3 here and these lower 3 right here. Simple enough. But what we want to have is the machine do it for us. So we'll come down here and we'll leave this. Leave that up for now, just so we can compare, I suppose. But soon we can just comment these 2 lines out because they're not really that necessary. So now what we want to do is actually feed this through and see if we get the results that we're expecting. So first we need to convert this data to a Numpy array. And a Numpy array is basically Python's version. An array is really just like a list of lists, only there's really no such thing as an array in Python. We're going to have to use Numpy to make an array, and Numpy is just a Python wrapper around C, so that's why we can get away with that. Anyway, moving right along, we're going to specify this as a capital X equals mp.array, and this will be an array of, like I said, a list of lists. And we have, man, I got an itchy neck. We have 1, 2, 3, 4, 5, 6 data points, which we could construe as features. So we have 1, 2, 3, 4, 5, and 6. And just for the sake of organization, I'll just do this. You can feel free to do what you want. So the first pair of coordinates was a 1 and a 2, right? So 1 and 2. And now we're going to do 5, 8, 1 point, and we'll add some spaces here, especially these decimals can get confusing. And then 1.5, 1.8. And then we had an 8 and an 8, a 1 and a 0.6, and then a 9 and 11. So that is our NumPy array of data, or again, as if they were features. Then what we're going to do is we're going to specify a lowercase KMeans, and that's going to be equal to capital K, capital M, means. And basically we're referencing this up here. Note the capital M, capital K there. So KMeans, and then we're just going to specify the n_clusters. So the number of clusters. So again, this is a flat clustering where we tell the machine learning algorithm how many clusters we want, and we know that this should result into 2 clusters, so we're going to notify the machine, hey, this is 2 clusters. So again, you know, say we're feeding it pictures of males and females, or pictures of dogs and cats, or features of dogs and cats. We want it clustered into 2 clusters. So that's what we'll do. Then we're going to call kmeans.fit, and we are going to fit the parameter of x. Okay, easy enough. Now, once we've done that, we're ready to move on, and we kind of want to visualize this. So at this point, we really don't need to do much else. We could print out our information and we'd have it, but it's kind of helpful, I think, to visualize the data, at least at first. So like I've said a lot in this series, even leading up to this point, there's a lot of machine learning, you actually will never visualize it yourself. You may visualize certain aspects, but the entirety of the operation won't be visualized. But like I also said, sometimes we actually use unsupervised machine learning specifically for the task of visualizing highly, like a lot of dimensions or a lot of features, and we kind of break it down simply just so we can visualize it and get the feeling at least that we're on the right track. But for the most part, you probably actually won't be graphing your results. But we will be here just simply for the educational effects of it. So kmeans.fit, and then now we're going to specify centroids. And so centroids are going to be the marker of the, I guess, the most ideal data point based on the points that we have. Okay, so when we do clustering, what we actually are doing is, or at least with KMeans, is we're going to be taking these points, and the way that we cluster them is we cluster them based on equal variance, okay, or degrees of variance, okay, so from, say, the others, right, on the plane. And so the centroid is going to be basically the center-ish kind of plot of all of those plots, let's say, in each cluster. So it would be like the ideal plot almost. So anyways, centroids, that'll be the center marker of the cluster. So centroids is going to equal kmeans.cluster underscore centers underscore. Don't forget that last underscore there. And then we're going to say labels, and labels are going to be literally the label that the algorithm is going to assign. So if you remember in our first run, if you went through with the SVM, the support vector machine here with supervised learning, we labeled the data, right? We said this was a 0, this was a 1, this was a 0, this was a 1, 0, 1, okay? And that's what we used to train the data, and then we could feed through a new data point and ask it, based on these features, please make a prediction, and it would. And with unsupervised machine learning, that's not the case. We're actually feeding it just this data, and we're telling the unsupervised machine learning algorithm, label this data. So this is where the term semi-unsupervised learning comes from, because what you can do is on the exact same data that we actually label later on, we can actually use unsupervised machine learning to label our data, and then we can move on to use supervised machine learning from that point onward. So keep that in mind. That's kind of semi-supervised machine learning, and maybe we'll have kind of a topic on that. A lot of your larger projects are going to be semi-supervised because machine learning is so powerful that you might find it's actually quite useful to solve a lot of questions. So you might find yourself actually mixing and matching quite a few algorithms to answer whatever your main project is. So anyways, moving along, labels. These are going to be the labels that the K-means algorithm actually supplies us. And ideally, our target, so to speak, is that it labels 0, 1, 0, 1, 0, 1, or it could label it as 1, 0, 1, 0, 1, 0. Anyways, moving right along, so once we have those, we can print, we'll just print them out just so we can see them with our eyeballs, Centroids, and then print labels. I don't know what I was thinking there. Anyway, so print labels. So now what we're going to do is we want to graph it. So again, at this point, the learning, not training, I almost said training. The learning is done, okay? The fitment is done, but we want to graph it. So now what we're going to do is we're going to say colors, and this is going to be a list of plot options, basically. And since we only have 2 categories, we really only need 2 colors. And so we're going to say G period and R period. G is the color green, period is kind of like a marker, and so it'll be just like a little period-looking marker. And then R period, same story there for red. Now what we're going to do is for x in range of the len of x. So the length of x is going to be 6, right? We've got 1, 2, 3, 4, 5, 6 coordinate pairs. So for each coordinate pair, well, actually, this is just for x in the range of 6. What do we want to do? Well, we're going to first, let's just print it out. Let's just say coordinate like that. We'll do coordinate colon and then capital X, X, so the x of x. This might be slightly confusing now that I think of it. Let's say for, I'm trying to think of a better variable that we could use, really. Could probably get by with like an underscore since it doesn't really matter. We could do like for underscore in range. You might see this underscore a lot. Underscore basically means it's a worthless variable. I kind of like, well, we'll use I. A lot of people use I. That'll be a good one. So for the ith of x, that's the coordinate. And then we're going to say the label, colon, and this is the label that the machine learning algorithm, K-means, has assigned to these coordinates based on its findings. And that will be labels I. Okay. And then what we're going to go ahead and do is plt.plot. And then we'll do x, I, and then the 0th, whoops, not the I, the 0th, and then the x, I, firsteth. And so what are these? X is corresponding to this Numpy array. So the x and then the ith element is either 0 through a 5. So this would be the 0th, the firsteth, second, third, and so on. And then the 0th of that would be just this, right? If we were talking about the 0th x, and then the 0th element of that would be a 1. So the x var in the plot and then the y var. So this, if I was 0, would be 2. So we're going to plot that. And then we're going to say the color of this plot is going to be, and we're using colors for color and marker basically. So the colors is going to equal, or I'm sorry, actually we're going to do colors like this, my bad. So colors responding to basically this, this colors array, so to speak, or list rather. So colors, and then what we're going to call is colors, and then we want the labels I of colors. So if you remember, we have 2 categories, therefore the labels could be either a 0 or a 1. So we're referencing either a 0 or a 1 element in the color list. So the 0th element would be a green, and the firsteth element would be a red. So that's it. Then finally, what we're going to say is marker size equals 10. And that will just kind of make the marker size a little larger than a tiny, pin plot, basically. So once we've done that, the next thing that we want to do is we're going to go ahead and scatter the centroids. So we're going to call plt.scatter. And we want to scatter the centroids, And we want to scatter this the X and Y version of Centroids, right? That's this right here. And if you recall, we have some fancy code for using NumPy or plotting NumPy arrays, and that would be colon, comma, and then the element, and then again colon, comma, and the element. So what this does is within the Centroids array, this is all of the 0th elements within that array. So this Centroids, this, let's say that we did actually X, this right here of X would be 151.5819, okay? So we're going to scatter those, and those are actually our Centroids. So what we want to go ahead and do is mark them, and we're going to mark them with an X. So their marker, basically the marker type, is going to be an X. The S for size, we'll call it 150. And then we'll say line widths equals, we'll do a 5, and Z order equals 10. So that should do. And then finally, we will call a plt.show. Okay, so barring any errors, which we're highly likely to have, that will be it. So let's run that bad boy. So this was the original plot. Let's exit that now. And okay, cool, we didn't have any errors. So here we have all of our stuff. And so here we can see as well, we have our coordinates and our labels. Anyway, so now you can see that this is the cluster of a group anyways. It's changing here. So in this instance, right, these are our zeros, and these, so I should probably move this over, and these are our ones, so these are zeros and ones, and these are the centroids, i.e. the center kind of marker between these points here. Now, what would happen if we did the following? What if we were rude and we said number of clusters equals 3? Now this means that we're going to have 3 labels. So we need to add another color. So let's add cyan. And that should do it as far as anything else we need to change. So now we're going to tell it, we're going to force it to choose 3 categories. Run it, there's the original. And now it has chosen 3 categories. And you can see here that this is still a category of its own. These 2 are a category. And then this is a final category that's being covered up by the centroid. But it is there. So what has happened here? Well, this is kind of how what I was talking about before, where how this kind of algorithm works. So these 3 are very close to each other. There's not a high degree of variance. Therefore, they're definitely a group. These 2 are closer than these 2, and certainly closer than these 2. Therefore, these 2 are paired together. And this one is all on its own because it's basically, obviously, further away from these 2 and definitely further away from these 3. So that's how you can kind of understand how this algorithm is actually working on the background. So if we said 4 categories, where do you think the centroids would be? Please write down your answers. Pop quiz class. No. So we'll add, let's add another argument here. We'll do yellow, period. And if we add a 4th category, well, it's obviously going to be these top ones right here. So we'll close out. And sure enough, yes. Because again, this one is further from this one, this one's further from this one, and this one is further from both of these. And of course, all of these are further from these. Therefore, these are chosen as their own group. So, equal variance. So anyways, that is it for the extreme basic introduction to flat clustering in terms of using K-means for unsupervised machine learning. In the next video, what we're going to cover is unsupervised machine learning using hierarchical classification or clustering to cluster into groups that the machine feels are the most applicable groups. So anyways, stay tuned for that. If you guys have any questions or comments on this video, please feel free to leave them below. Otherwise, as always, thanks for watching. Thanks for all the support and the subscriptions. And until next time.